Good day. This lecture is going to be about the presentation of data into tabular form. So the objective with the presentation of data is to develop tables and charts for categorical data, and as well as for you to do the same for numerical data and to look at the principles of property of presenting graphs. Now this gives an overview of tables and graphs on how we need to present them. In the first place, we have data, and this data needs to be presented in tabular form or graphical form. In tabular form, we only have the constituency table, summary table, or frequency table. It's still one and the same thing. And on the graphical part, we have the bar charts. That is the simple bar chart, multiple bar chart, the compound bar chart, also known as composite or component bar chart. And then we move over to the pie chart, histogram, and ogive. And then the third group is the parental diagram, frequency polygon, and stem and leaf. So this is what we are going to go through, the presentation of data by tables and graphs. But this lecture only focuses on the presentation of tabular form. So the reason for us to use a constituency table is to condense the raw data into a more useful form, and it allows for a quick visual interpretation of the data, due to the fact that this allows us to see the major characteristics of the data set, where it's concentrated and where it's clustered, or if there's any outliers in the data set. Now, a constituency table or frequency table is self-explanatory, implying that it has a title, column headings, or row headings where applicable, and have classes or class intervals, and it shows the frequencies which falls within each class or class interval. Now this one is an example of a categorical data, on how categorical data is summarized in a frequency distribution table. Now in this case, it gives you the categories, the frequencies, and the percentages, so that you can see the differences between the categories. Now on the numerical aspect, you now have class intervals instead of categories. Those categories are now transformed into class intervals. So in these intervals, they are ordered groupings from the smallest interval to the largest, and the frequencies falling within each intervals is displayed, and you can also make use of the tally marks to represent the frequencies. Now there's certain things you need to take into consideration when it comes to the numerical presentation of data. That your groupings should be between 5 and 12. That means your classes, your class groupings should be greater or equals to 5 and less than or equals to 12, not beyond. So this one is what we are going to use as a rule of thumb. Now to determine the width of your class intervals, we divide the range by the number of class groupings that we want. The range, as we all know, is the highest value minus the lowest value. Now in constructing a frequency distribution, you'll be given a sample data. Within that sample data, then you'll be told how many classes you need, so that at the end of the day we all have a uniform representation of the data. So you are given the class intervals, the number of classes that you need, and that you are going to use as well to determine the width of your class. To determine the width is whereby we make use of the range divided by the number of classes. Once we have determined the class limits for each class, then this becomes easier for us to interpret and to group our values into classes. Now this can also give us the relative frequencies, which is the frequency divided by 100 by the total times 100. That gives us the relative frequency percentage, whereby the relative frequency is just the frequency divided by the total frequency. Now, before you start grouping your observations, there's two cases that needs to be met. That is, your classes must be exhaustive and mutually exclusive. So exhaustive means each possible observation should find a class to belong to. It should be grouped into a class. And then mutually exclusive means that no two classes or class intervals should overlap. Now, class intervals are applicable only to quantitative data, while classes apply to both quantitative and qualitative data. Class intervals should be, take note, should be of the same sizes, except for the first and the last open-ended classes that are supposed to take care of any possible outliers. And as well, in cases where you have extreme outliers, then your last classes, the last 3 or 2 classes, can have different class width from the rest. Those are the only 2 cases where the class intervals differ in size. Now, an outlier is a value that is not consistent with the rest of the values that exist in a data set by being either too small or too big. These are the extreme values in our data set that are not clustered together with the rest. Hence the name extreme. They lie at the extreme ends of our distribution. Now, making the class intervals open and closed-ended enables us to have exhaustive classes. Now, before we can also make use of the constituency table in drawing it, we need to familiarize ourselves with class limits, class boundaries, and the class width. Now, the class limits are the beginning and end numbers of a class interval. And the class boundaries are the points where one class begins and the other one ends. So, if, for example, you have class intervals of 20 to 29. 20 will be your lower class limit, 29 will be your upper class limit, because this is where the end points, these are the end points. But for the same interval of 20 to 29, if you look at the class boundaries for this interval, 19.5 will be the lowest class boundary, and 29.5 will be the upper class boundary. So the 19.5 in actual words tells you where now the one class begins and the other one ends. Vice versa, the 29.5 also tells you where one class begins and where the other one ends. So the class width literally states the width of a class interval under discussion. So this is the range that of your class interval. And to obtain this class width is whereby we take the upper class boundary minus the lower class boundary. Now this is just the steps again in using the class intervals in constructing our frequency distribution table or the constituency table. Now in the first step we decide on the number of class intervals that we need to have. This is guided by the fact that it should lie between 5 and 12 inclusive. And then thereafter we need to obtain our range by calculating it, taking the smallest value in the data set from the largest one. And then step 3, we divide the range by the number of classes that we have decided upon in step 1. And then once we have decided that, we decide now on a appropriate class width that is determined by step 3. Now the class width that we have, it's in the multiples of 5 or 10. Okay. And then we utilize the class width that we have decided upon in step 4 to set up class intervals starting with the lowest limit that is close to as possible to the smallest value in the data set, or it can be the smallest value itself, or you are given what the starting point should be for consistency sake. Now step 6 is where we make use of the tally to discuss, as discussed earlier, to count how many observations fall into each class interval. So the tally marks, after you have done your tally marks, you add them up and it gives you your frequencies. Now the following parts just gives us on how the calculations go and the formulas that we need to go, as we've already touched base on them. Now a class mark is the midpoint of a class interval. Now the class mark is obtained by adding together either the class limits or the class boundaries of a class interval and dividing the sum of 2. So the midpoint of the class mark, once again, you can either use the class limits or class boundaries. It will give you the same midpoint. So you take the summation of the upper class limit and the lower class limit, divide by 2. It gives you the midpoint. Or you take the lower class boundary plus the upper class boundary, and it also gives you the midpoint, the class mark. Now, in deciding the class width, there's also a scientific way of determining the class width, and that scientific way make uses of the Stigers formula, where now you take the class width to be the range over 1 plus the natural logarithm of n, or you can now just say it's the range over 1 plus 1.44 ln n. So this one now gives you the class width. Now where in this formula you have n, n is now the number of observations that you have in your data set. So that means if you are told to use the Stigers rule, then you make use of the Stigers rule. Or otherwise, we use the default by taking the range over the number of observations. The Stigers rule is only used when you are told to do so. In practice, as we have said, it's good enough to decide somewhat arbitrarily how many class intervals to use, guided by the principle that on average there should be less than 5 observations in each class interval. So k in this case gives us the average number of observations in the class intervals. So in deciding this factor is whereby you take the number of observations divided by the number of class intervals, and this should be giving you a factor of greater or equals to 5. Now let's use an example to illustrate this. A manufacturer of insulation randomly selects 20 winter days and records the daily high temperatures. Given this raw data, we are now going to make use of it to construct a frequency distribution table. Now you sort your data in ascending order. It makes it easier for you to pick out the lowest value and the highest value in your data set. And if they are clearly evident, then there's no need for you to sort out the data in ascending order, but it's for simplicity. Now the next step is we find the range. From the given data set, we see that the highest value is 58 and the lowest value is 12. Subtracting these two, 58 minus 12 gives us 46. Now we select the number of classes. In this case we take 5. And we take note, our classes are usually between 5 and 12, being inclusive. Now with 5 classes, we take the 46, we divide it by 5, it gives us 9.2. This now can be rounded up to 10, since our width is in the multiples of 5 or multiples of 10. So now we decide that our width is 10. Now we go ahead to determine now the class boundaries. In this case, we are saying that starting with 10 as the first class limit. If we take 10 as the class limit and our width is of 10, then the class limits are going to be 10, 20, 30, 40, 50, 60 for those ones respectively. Okay, and then to compute our class midpoints is whereby now we take the endpoints of each class limit, and that gives us 15, 25, 35, 45 and 55, and then we count each of the observations which falls within the class intervals, and that gives us something like this. So the first class that we have said, starting with 10, is from 10 to 19. Then the next one is 20 to 29. Then we have 30 to 39. Then we have 40 to 49. And then 50 to 59. So the less than factor is just one value less. So we have this. Those are now our class intervals. With the class intervals of such that we have, there are class boundaries in 10. If we take the first one, the class boundaries are going to be 9.5 to 19.5, and then the next class will start off at 19.5 to 29.5, 29.5 to 39.5, and so forth. So that is now how we go about it. And if we counted our frequencies, that gives us the frequencies. From there onwards, we can now also calculate the relative frequency and the relative percentage. Now the relative frequency is just the raw frequency count in each class divided by the total number of observation. That is our n now. And then the relative percentage is just taking the relative frequency, multiplying it with 100. Now, things that you should remember why we should always, at the end of the day, as a class, come to the same conclusion. So that regardless of whatever each one will do, we'll always come to the same conclusion or to the same frequency distribution that you have to draw. Because different class boundaries may provide different pictures of the same data. And then shift in data concentration may show up when different class boundaries are chosen. As the size of the data set increases, the impact of alterations in the selection of class boundaries is greatly reduced. Now, when comparing two or more groups with different sample sizes, you must use either a relative frequency or a percentage distribution. So this is now the reasons why at the end of the day, at least you should be told the number of classes that you are working with, so that at the end of the day we all construct the same frequency distribution given the number of classes and the starting point. So thereafter everything for everyone else will be the same. Now the cumulative frequency and relative frequency are other features that come into handy in manipulating of data that are presented in a constituency table, whereby the cumulative frequency is where we start adding from the first frequency, adding up the next one up to the next, where we come to the last group. It should give us the total of the frequencies. So in using the previous example, calculating the cumulative frequency, we take the first frequency, that is now 3, plus 6 gives us 9, 9 plus 5 gives us 14, 14 plus 4 gives us 18, and 18 plus 2 gives us 20, whereby 20 is the total of the frequencies, whereby the cumulative percentage is taking the first percentage as well and adding the next and the next until it gives us to 100. But take note, your cumulative percentage will not always give you 100%. This is due to rounding off error and calculation error. So you should get a value that can be 100.01 or even 100.1 or 99.9 or 99.0099 or anything that is close to 100 due to error that has been committed in your calculations due to the rounding of error. That brings us now to the end of the presentation.